silicon silicon p-type 100 in KICHE fall meeting. So let me first introduce the contents of my presentation. First I will tell what is the aim, means what target of my study. Second, basics in HFCVD process. Third one, experimental apparatus. And fourth, result and discussion. Lastly, I will conclude about the results. So here the target of my study is growth of high density diamond on silicon substrate, which is a non-diamond substrate. So here I use some pre-treatments. First one is I use scratching with diamond paste, and by scratching it gives some residual stress on residual seeded in the substrate surface. So it creates some sites for nucleation. And also by this scratching there is also one disadvantage. It creates a mechanical damage or substrate. So many researchers use for that problem, they use the coating, over coating, some type of buffer layer. So here we use the zinc as a buffer layer to overcome that type of problem. So zinc is also very interesting here because zinc has the melting point 419, but our substrate temperature is 750. So probably there is evaporation of zinc. But here the case is something different. We are the substrate first takes the liquid phase, So substrate first initial growth, the substrate is liquid type, and it increases, it enhances the diamond nucleation. Also here we use the experimental details for my study. Here we use p silicon vapor. We use the deposition of zinc film separately by thermal evaporation, and the vacuum was kept 10 raised per minus in that chamber, and then the zinc film was loaded in a hot filament chemical vapor deposition. Here our system is very strong, means we have our system, hot filament chemical vapor system, is equipped with world's famous tool like XPS, X-ray photoelectron spectroscopy. So by this equipment we can transfer our sample into analysis chamber without exposing the sample outside. So the chamber vacuum is kept 10 raised per minus 9. So here I will briefly tell about the HFCVD process, in which first proposed this HFCVD first proposed by Japanese scientists and his co-workers. They use the tungsten filament, and I also use the tungsten filament here. The aim of this is dissociate of molecular hydrogen into atomic hydrogen. So here atomic hydrogen plays 3 roles. It converts, it reacts with, or it reacts with, and also it creates graphite phase, and by this graphite phase we can remove graphite phase from the substrate, and there will be chance for clusters with diamond on the substrate. This hydrogen atomic hydrogen also sterilize the diamond surface or sp3 and it remains for whole growth. Here is our HFCVD system. We use the turbomolecular pump and the vacuum we got here is 10 raised power minus 7. So we also equipped here is to analysis chamber. So we can see the analysis. It is our HFCVD system and XPS system. So here after doing deposition diamond, we are using this gate to transfer the sample to XPS analysis. So here is no exposure, the sample is not to be exposed outside. So this is very good, and I think our system is very much good as far as the equipment, very sophisticated equipment is attached to our system. It is overview of our XPS and HFCVD system. As far as results and discussion are concerned, from atomic force microscopy image are scratched one without deposition. So we can see here that there is randomly scratched, the surface is scratched, and we can see also particles here. So here the root mean square roughness is 2.5 nanometer. Then we evaporate the zinc on the substrate and we also analyze by AFM and we got this type of image. So here we can also observe the scratches. So this indicates that the film is thin. It is not so much thick. We can also, that is why we can see the scratches here. This to see the morphology again by scanning electron microscopy, the scratched one which has the diamond growth and the crystals are big and there are voids also in the picture. As far as zinc is concerned, zinc layer, and also this is the AFM image for that one, the scratched silicon. We can see here the diamond growth and also the size of particle is 1.5 micrometer and also the roughness is 88 nanometers. This scanning electron microscopy image is on zinc film. We use here zinc as a buffer layer, so you can see it is evident from the picture that there is high density growth film here and crystals are very small and very uniform. All crystals are 111 plane, having 111 plane. As far as AFM atomic force microscopy image for that substrate sample, we can see here the morphology of the sample, and here we can see the roughness is 71 nanometer and the particle size is below 1 micron. So here diamond film surface is smoother than that of diamond on scratched silicon, and film is also denser on dense silicon scratched silicon. We can support our samples, our results by micro Raman also. Here we can see the micro Raman images of zinc on scratched silicon and also without zinc layer. So here it is evident that there is symmetric and sharp peak at 1333 and both the films have good quality diamond. But here is non-diamond background also present from 13.50 to 17. It indicates there is amorphous diamond and graphite sp2 graphite diamond with sp2 and sp3. So as compared to scratched silicon, there is prominent peak at 1605 at this place. So this peak is disordered graphite peak. The original peak is at 1615. So this is disordered peak here, graphitic peak. So by this Raman analysis, we can conclude that the film grown on zinc is good quality film. Here we can conclude our results. An attempt is made to enhance the nucleation of diamond using zinc as a buffer layer. Zinc layer acts as a liquid film for the initial nucleation of diamond. A complex metal silicon hydrogen carbon is may be able to create an appropriate deposition condition for diamond film growth. It would be interesting to investigate further initial stages of growth in such a complex system, which is currently in progress in our laboratory. And there is also need to investigate the variation in thickness, and also this variation in thickness can also affect the growth of the diamond growth. And my acknowledgement is to Joseph, graduate student fellowship.